Today we are going to discuss about the topic photoelectric effect. And this phenomenon of photoelectric emission was discovered in 1887 by Heinrich Hertz, and later it was explained by Albert Einstein. Now let us explain what is photoelectric effect. Here we have a metal surface, and when a light of suitable frequency, when a light is incidenting on this metal surface, the electrons will get ejected from the metal surface. So this phenomenon is called photoelectric effect, and the ejected electrons are called photoelectrons. Now let's check the experimental setup to observe this photoelectric emission. For that we need a quartz tube. It's an evacuated tube, and here we have two electrodes, and these two electrodes are connected by, there is a cell is connected in between these two electrodes, so we can apply some potential in between. There is some kind of potential difference between these two electrodes, and when light is incidenting on one of the electrode, the electrons will get ejected from this electrode and it will move towards the other electrode. So there is some movement of electrons, so current will be formed here. So that current formed due to the photoelectrons is called photoelectric current, and this current can be measured using a meter connected here, and this photoelectric current will be of very small value. It is of milliampere range, and here we can change the different parameters here. We can change the intensity of the light and also the frequency of light, and we can also change the potential difference applied between the two electrodes. So in today's class we are going to study about the difference in change. We are going to study about the changes observed in the photoelectric current by changing the different parameters here. So let us first discuss about the effect of intensity of light on the photoelectric current. Here we are going to change the intensity of light and to find the changes in the photoelectric current. Need effect simulation. We are using effect simulation. So here I am going to change the intensity of light. When the intensity of light is minimum, you can see that if light is minimum, if it is 0, then no photoelectrons are emitted. And if I am changing the intensity, you can see the photoelectrons are getting emitted, and the current is 0.029 ampere. And as the intensity of light increases, we can observe more photoelectrons are getting emitted and more photoelectric current is produced. Here the current is also increasing when I am changing the intensity to maximum. So from this we can see that intensity of light is directly proportional to the photo current is directly proportional to the intensity of light, and we can get a graph like this. Here we can say photoelectric current is directly proportional to the intensity of light. Next we can discuss about the effect of potential on photoelectric current. For that, if I am changing the potential to one side, if I am changing the potential, if I am increasing the potential, you can see the current also increases and it reaches to a maximum value. Now there is no change in the current. The current reaches to a maximum value, and it remains constant. It remains constant in as 0.114 ampere. So this value is called saturation current. And if I am changing the potential in the reverse direction, now you can see the photoelectric current reaches to 0, and you can see that the photoelectrons are no longer entering into the other electrode. It cannot enter into the other electrode. This value of the potential is called stopping potential. As you can see in this graph, when the potential increases in this side, it reaches to a maximum value of current, and that current is called saturation current. And if I am increasing the potential in the opposite direction, the photoelectric current reduces and it reaches to 0, and when the current reaches to 0, the corresponding value of the potential is called stopping potential. Now we can discuss about the intensity. Now I am going to vary the intensity. Here we know the saturation current is 0.61 ampere, and if I am increasing the intensity of light, then you can see the saturation current is also increasing. And if I am decreasing the saturation current, so if I am decreasing the intensity, the saturation current is also decreasing. So we can say the saturation current depends on the intensity. If I am increasing the intensity, saturation current also increases. Next, in the case of stopping potential, if I am changing the intensity, here stopping potential is minus 4 volt. So if I am increasing the intensity, the stopping potential will not change. It remains as the constant. So we can say the stopping potential is independent of the intensity of light. So we can conclude the saturation current is found to be large at higher intensity. As intensity increases, the saturation current also increases. And the stopping potential remains constant for different intensities. So the incident radiation, the stopping potential is independent of its intensity. And we can say the stopping potential is sufficient to repel the electron with maximum kinetic energy. So we can say EV0 is equal to kinetic energy maximum, where V0 is the stopping potential. Next, we can discuss about the effect of frequency of the incident light on the stopping potential. In the previous case, we have seen the stopping potential is independent on the intensity of light. Now let us discuss about the effect of frequency of the light on stopping potential. So here you can see the stopping potential is minus 2.8 volt. Now I am going to increase the frequency. So by increasing the frequency, you can see that the 2.8 is not the stopping potential. That means the stopping potential is increased. So we can say the stopping potential increases with the frequency of the light. So we can conclude that the stopping potential increases with the frequency of light, and the saturation current is independent of the frequency of light. But here the stopping potential depends on the frequency of the light. So we can say the kinetic energy depends on the frequency of the incident light. We know kinetic energy is E into stopping potential. So stopping potential is depending on the frequency of light. So we can say kinetic energy will depend on the frequency of the incident light. So there exists a certain minimum cutoff frequency μ0 for which the stopping potential is 0. So we can conclude that the laws of photoelectric emission, that means as the intensity of light increases, the photoelectric current also increases. And in the second case, we have seen as the frequency of the incident light increases, the kinetic energy of the photoelectrons also increases. And the photoelectric effect does not occur if the frequency is below some certain value, and that value of frequency is called the cutoff frequency or threshold frequency. Thank you.